Hi and welcome to this Leaving Certificate Applied Maths video. Today we're looking at forces and specifically creating differential equations. So in this video, we're going to build on the work we've already done on forces, and we're going to look at the setup of differential equations that contain forces. So we're not going to be solving any differential equations here. It's merely just the setup. So we're going to use Newton's second law as our starting point. We're going to use F equals ma, and we're also going to be bringing power into this. So it's just to remember power is equal to force by velocity. Or for a way to convert your power into a force, we're going to do power divided by velocity. So the first thing you want to do is, if you're given power, you want to convert it to the force using this relationship. This gives you a driving force usually, so some kind of force from an engine or a motor, and will generally be used along with other forces that you're given. Then I would advise you to draw a force diagram, show all the forces acting in the direction of motion. So we're talking parallel to that direction of motion, and if you need to, make sure you resolve them. We are focusing on driving force, a resistance force, and gravity. So the difference here between a normal F equals ma question is we're going to have some kind of variable force. Make sure you label all of your forces and make sure you label the direction of motion or the direction of acceleration, just like we will with our normal force diagrams. Then we apply our F equals ma and make sure that any forces going with that motion or with acceleration are positive and against them are taken as negative. Finally, because we're working with differential equations, you want to replace a with whichever differential coefficient we are advised to do. So that will be given in the question. So it's either going to be a is equal to dv dt, so the rate of change of velocity, or v dv ds. So that's a way of connecting our velocity to displacement. So question 1, a car of mass 1000 kg is moving along a straight level road. The brakes are applied at a force of minus kV and air resistance is minus 0.5 v squared. The engine is off, and show that this differential equation is correct. So we can see here that the force being applied by the brakes is minus kV, which means it's proportional to the velocity, so it's not a constant. So there is no, all we're given is forces. There is no power or anything like that given, so we're going to go straight to our force diagram. We have weight, which is acting down. Anytime I do a force diagram, I do make sure that it's complete, even if you think, oh, do we really need that information? It's a good habit to put everything in. We then have our reaction, which is equal to the weight because there's nothing else acting on it. We then have a force due to the brakes, which is kV, and then air resistance as well, which is 0.5 v squared. And I put them both that way because I'm saying our acceleration is really in that direction. Or really what I'm saying is the movement is that direction because it's a deceleration that we're experiencing. So when we put this together, we're going to use F equals ma. And because we have the kV and the 0.5 v squared going against the direction of motion, they're both going to be negative. That's why it's so important to have that direction of motion in there. And the mass is 1000 times A. So the last step we need to do is we need to see what they replaced A with. In this question, they used V dV ds. So that's going to give us our 1000. Change your A to V dV ds. And that equals minus kV minus 0.5 v squared, which is exactly what we were asked to do. So example 2, a motorbike of mass 60 kg is climbing a hill inclined at an angle theta to the horizontal, where sine theta is 1/20. The engine provides 15 kilowatts of power and the total resistance force, including gravity and friction, is 20V plus 600 G sine theta newtons. Show that this is true. So we do have a power here. So we have 15 kilowatts of power, so that's P. So we're going to put this into SI units, which is getting rid of that kilo, and into watts. In terms of a force, we're going to have power divided by velocity, which is going to make this 15,000 divided by V. So now when we're putting that onto our diagram, we have a force rather than power. So we have a motorbike climbing a hill, so we get a scenario that looks like this. Now, I haven't all my forces in here, but we are moving up the hill. It does say climbing a hill, so there's my acceleration. I have the weight acting straight down, which is going to be 600 G. I don't know my reaction straight off. And then I have a force pulling it up the hill. Now, usually what we do is we would resolve weight and we would figure out what part of weight is pulling it back down the hill, friction and so on. However, this question told us that there is a full resistive force there of 20V plus the gravity piece. This is or the weight part. So that is the horizontal component. And when I say, sorry, the component of weight parallel to the direction of movement. So there really is a 20V there. So we don't need to overcomplicate it with this diagram. We can do something much simpler. We have part of the weight, which is acting down. That's going to be W cos theta. We then have reaction, which is going to be equal to that. If you need to go back over resolving your weight on inclines, the force video is linked in the description below. We then have this tractive force, this like force that's pushing it forward, and we have this full resistive force, which is 20V plus 600 G sine theta, and there's our direction of motion. So this diagram is actually not needed at all because they've given us that total resistance force. So we're going to use just our F equals MA. Our direction of motion is positive. So that gives us 15000 all over V minus 20V. And you put this in a bracket plus 600 G sine theta, and that is going to be equal to M, which is 600 times A. We have a little bit of work to do because we need to fill in what sine theta is, and we need to change our A, so let's give ourselves a bit more space. So now this is all a little bit clearer. You can see what's going on. So we need to figure out first what's happening with our A. So A is going in as dV dt. You can see that we don't have a fraction over here, so we've obviously multiplied that out. They've actually left this in terms of sine theta, so we will too. And we just need to clean up a bit on our signs. So we're going to multiply across by V, which is going to give us our 15,000 minus 20V squared. And we're going to bring in this minus as well, so that gives us 600 G V sine theta, and that equals 600 V A. And then all we need to do is change our A, so I'm going to flip it so it looks the same. So our 600V, we then put in dV dt for our A, then we have 15,000 minus 20V squared minus 600 GV sine theta, and that's exactly what they want. So in these kind of questions, and we're going to look at some exam questions in a second, but in these kind of questions, you want to keep an eye on what format they want, maybe where they've got the numbers from, but don't focus too much on your end result at the start. Focus on really building that from your F equals MA. So example 3, a cyclist and a bike together have a mass of 80 kg. The cyclist is moving along a level road with wind resistance modeled by R equals kV squared. The cyclist pedals at a constant power output of 400 watts. So first thing we're going to do, we've been given power, which is 400 watts. We're going to convert that into a force. Our formula is power divided by velocity. So 400 divided by V. Then I'm going to draw this out. So this is basically all the forces that we have. We have weight, which is acting down. We have reaction. I'm not going to use or because they've used or for resistance. So reaction is equal to the weight. We can put that in. That's going to be ATG, and that's going to be the same. We then have this tractive force. So the force pushing it forward, which is 400 over V, and then a resistance force, which is kV squared. We then have our direction of movement as this. So our A is pushing us forward. So then let's set up our equation using F equals MA. The direction of movement is positive, so that gives us 400 over V minus kV squared equals mass times acceleration. So if we take a look at what they want us to do, we've replaced our A with dV dt. Be careful not to think it's V dV dt. There's no such replacement. A is either dV dt or V dV ds. We don't have a fraction though on the right hand side, so we're going to multiply across by V. So that gives us 400 minus kV squared equals 80 VA, and now we're going to replace our A. So 80 V, and then we put in dV dt is equal to 400 minus, I missed a cubed up here, so minus kV cubed. Questions like this are really nice because they show you what the answer should be. So even if you don't get it worked out, you can still move on to the solving element of it. If you want to revise how to solve differential equations, I've linked all the series videos in the description below. So this is question 9, part B, part 1 from the 2025 exam craft mock. And it's a great example of how this will be asked in an exam situation. And it's not very different from those earlier questions in the video. So a car of mass 800 kg is moving along a straight horizontal road with an engine of the car working at 20 kilowatts. So we've been given our power as 20 kilowatts. That's the same as 20,000 watts. And in a question like this, we need to turn that into a force. So our force is power divided by velocity. So that's going to be 20,000 divided by V. The next thing we're told is the total resistance to the motion is 25 V newtons, where V is the speed of the car in meters per second after t seconds. So show that this is true. So let's draw out our diagram. We will have weight, which is going to be 800 G. We have a reaction, which is going to be equal because it's on horizontal ground. We then have that tractive force that's pulling it forward. So we've already worked that out. It's linked to that power that we've been given. And then finally we have the resistive force, which is 25 V. And then we have A showing the direction of movement. We're then going to have F equals MA, and that's going to be what's pushing it forward. So the 20,000 divided by V, take away the resistance, and that is equal to mass, which is 800 times A. So focusing on what we have versus what they've given us, it looks quite different. But the first thing I'm going to notice is that there's no fraction over here on this side. So let's get rid of the V by multiplying across by V. So that's going to give us 800 VA. Our A in this question has been changed to dV dt, and you can see that the coefficient in front of the dV dt is 32V. We currently have an 800. So it's like we've divided across by something. So the easiest way to spot what we're dividing across by is the V squared does not have a coefficient, but here it has 25. So let's divide everything here by our 25. And that's going to give us, this gives us 800 minus V squared equals 32VA. And we are nearly there. Our last step then is to simply change our A to dV dt. And that's 800 minus v squared, which is exactly what we want. So in some of these diagrams, I've put my resistive force as being on this side, so like pushing it back. That's absolutely fine to do. Equally, if you wanted to simply put it as a force going that way from that side, exactly the same. As long as you get that direction and show that correctly, it doesn't matter how you show it on your diagram. Often with resistance, we kind of nearly show it coming from the front rather than coming from the middle, but it is completely up to you. The question is about getting to that differential equation. So however best you will work, that's the best way to do it. So this is question 4 from the 2023 higher level paper. A ball of mass mkg is projected with initial velocity 15 meters per second vertically downwards into a tank of water. The ball travels through the water against an upward buoyancy force that's 4 times the magnitude of the weight of the ball and a drag force of mv squared. Draw a diagram to show the forces acting on the ball while moving downwards through the water, and that's important. Okay, so we're moving down through the water. So here's our ball. We have our weight, which is acting down. So weight is equal to mg. And then we have 2 forces pushing it up. So it's an upward buoyancy force that is 4 times the magnitude of weight. So that is my buoyancy, which is 4 mg. And then we are working downwards. So there is my movement downwards. So then the drag force will always oppose motion. So there's our drag, which is mv squared. This velocity doesn't come into it. Okay, it does not come into it. Velocity does not belong on a force diagram. Only forces belong. So there are 3 forces. We have weight, we have buoyancy, we have drag. So then part 2 says that show while the ball is moving downwards, the rate of change of its velocity with respect to its distance below the surface can be expressed as this differential equation. So again, all we're focusing on is F equals ma. Our movement is downwards, so we take downwards as positive. So we have mg minus what's upward, minus 4mg minus mv squared is equal to mass times acceleration. So here, all the masses, m is going to actually cancel out, leaving us with g minus 4g, so minus 3g minus v squared is equal to acceleration. We can see here from the question that they've used v dv ds. So we get v dv ds is equal to minus 3g minus v squared. We're very close to the answer that they want. All that they've done is they've actually substituted in, instead of g, are 9.8, which is where they got their final answer, v dv ds equals minus 29.4 minus v squared. So I've skipped some parts in between that we're actually solving that differential equation, but if you want to go through that in more detail, the actual solving of it, I've linked the video that goes through this full question in the description below. But it tells us then after reaching its maximum depth, the ball changes direction and begins to move upwards through the water. Draw a diagram to show the forces acting on the ball while it's moving upwards through the water. So here's our ball, and we always have weight acting down. So weight is equal to mg. We then have a buoyancy force which works upwards. As before, the buoyancy is 4 mg. Now, the difference is this time we're moving upwards through the water. So when I put in my arrow with an A, what I'm really saying is that's my direction of motion. So that A may be positive, it may be negative, but that's my direction of motion. And putting that in just really, really helps to make sense of our F equals ma, which are positive, which are negative, and so on. So don't overthink that about, oh, well, technically the acceleration is going the other way because it's decelerating. In the majority of cases, it is the direction of motion. The only time that won't be the case is if we're dealing with circular motion. Then it's a true acceleration. But other than that, think of it as your direction of motion. It simplifies the whole thing. So because we're moving upwards, our pushbacks, the drag in this case is actually going to oppose it. So there is our mv squared coming back down. So now we're asked to write a differential equation for this particular scenario. Now, unfortunately, they don't give us the answer, but we know what the last one was, so it's going to be very, very similar. So F, our force. So we start with our force up, so 4mg, minus our force down, so minus mg minus mv squared is equal to ma. And then our m's all cancel out, so that gives us 3g minus v squared is equal to a. We're going to focus on the fact they asked for the rate of change of velocity. Rate of change without any other qualifiers is basically our dv dt. So here we're going to sub in our 9.8 minus v squared, and that's going to be replaced with dv dt. So if it said the rate of change of velocity with respect to something, then it might be different. If they just say rate of change, we're talking dv dt. So we are going to get, change back, 29.4 minus v squared is equal to dv dt. Or if you want to put that bit first, dv dt is 29.4 minus v squared. So very similar to our last part, but the direction will change our sign of one, but really the interaction of the whole thing. We do need a new force diagram, which they did ask you to draw, which was nice and led you through the question in a nice way. So our final question in this video is question 4 from the 2024 higher level paper, and we're looking at part 4 and part 5. So the little introduction to the question tells us that there is a snowboarder of mass m and is traveling with velocity v1 when he enters a circular arc AB at a point A. It tells us AB is a radius of 6.7 at a center C. ABC lie in a vertical plane, and AC is vertical and BC is horizontal. And a student models the motion of the snowboarder, ignoring the effects of friction and air resistance. But then we get to this question, and this part of the question, and it tells us that at point B, the snowboarder leaves the arc and moves vertically through the air. The student wishes to calculate V, the velocity of the snowboarder, t seconds after he leaves the arc. The force due to air resistance is now modeled as mkV. Draw a diagram to show the forces acting on the snowboarder as he's moving upwards through the air. So here's our snowboarder. As always, we have weight acting down. So our weight is mass times gravity. So we have mg. The snowboarder is moving upwards, so there's our A, which means that the air resistance is opposing motion. So here is our mkV. So when we're working with this diagram, part 5 asks us to create this differential equation, which is the rate of change of velocity with respect to time. We start with our F equals ma. Our forces, so we're taking upward as positive because that's the direction of motion. So we get minus mkV minus mg is equal to ma. The m's disappear, and we can kind of see where we're at now. So acceleration is equal to, I'll bring my a over, minus, they pull the minus out in front, gravity comes first plus kv, and then the last step is to replace our a with our dv dt. So we have dv dt is equal to minus g plus kv. So these are quite nice questions. You just need to have a little bit of practice with them. If you want to see this 2024 question 4 done in full, I've linked the full video in the description below.